Very much, and thank you for the invitation. I'm glad that we can be present here as one of the tree consultants associations, the SAG Tree Statics, and more or less parallel to what happened here in the standards work. We also decided to come up with a standard specifically for the static test method. For those of you who are familiar with the static load test method, that of course is boring now. I'll just give a brief introduction about where it all comes from. And if we look back in history, there have been always people pulling trees to failure to analyze and get an idea how strong trees are. That is not what we as tree consultants can do. Our clients don't like it if we tell them afterwards how strong the tree was. So we only pull non-destructively on trees. And the first idea is that it would be able, for example, to assess the strength of a stem from how much you compress the fibers as you bend the stem. What I know found goes back to the 50s, Arno Ilinen, who has that in one of his papers from the 1950s, this idea. It all catched up speed in the middle 80s in Germany, where a landscape architect called Günther Sinn idea that it would be possible to analyze the safety, the risk of failure of trees, the same way that engineers assess buildings and other structures, man-made structures. And this was a time where Professor Frei Otto in Stuttgart was an engineer and architect who studied natural constructions. So they got together, so to say, with the idea, if you, Mr. Otto, are able to design buildings according to the way that plants and trees grow, why shouldn't it be possible to go the other way around and say, if we have a tree and want to understand if it's strong enough to withstand a storm, we can apply the same principles that apply to engineering structures. And this was then carried out in a state-funded project under the direction of Lothar Wessely at the University of Stuttgart. And later on, both Günther Sinn and his son Thomas Sinn and Lothar Wessely continued these ideas of the pulling test method in two different... Oh, okay, this is... I try to be speaking, if I speak constantly, it seems to, probably it's AI behind it that realizes if someone is not talking. So today we have established pulling test methods. We termed it a static load test method because this pulling test is defined in experimental mechanics as you pull on something until it breaks, and that's not what we really do. The idea is if you have a tree that has a problem with some defects, and we just learned that not all defects are a sign for a risk of failure, and this is what you can also see if you pull many trees with this method, that you get a certain relaxation. You're not so stressed anymore about defects if you find out how strong these trees are still, even though they have severe defects. The way we find out if they're strong enough or not is we pull on the tree. So it is a pulling test. But we actually generate a bending. So someone climbs up the tree, installs a rope, and then you find another tree or a lorry, and then you use a winch or any other device to generate force and exert forces on this anchor point in the tree. In order to be sure that we not only watch what happens, because you don't see much the way we pull the tree, we're pulling non-destructively, so actually nothing's visible in the tree when the pulling test is carried out. You use high-resolution sensors that allow you to really monitor how the tree responds to that load. And this is, as I mentioned, a strain measure, an instrument that measures the fiber compression or extension as we bend the stem. And the second instrument is called an inclinometer, which is nothing else than a digital lever. So you can measure changes in angle at the base of the stem as we move the tree in the soil. And of course, I already said it is a non-destructive method. We have to limit this movement to a degree that is not causing irreversible changes in the structure. At the same time, we measure constantly the force that's exerted on the tree with force meter or dynamometer. This is a standard device to measure tensile forces, nothing special about this. And the idea behind the entire method is to establish a correlation between the applied force and the tree's response. So the pulling test itself, what you see when we go to the tree and pull it, only serves to establish this correlation. If I pull with a certain force, how does the tree that? Well, should we change? Okay, this is much better. No, okay, we'll try it. Maybe we keep changing all the time then. This is a setup from a rather special tree. It was first, it was treated by tree surgeons who built a brick wall inside, and then an artist came and made it into a piece of art. And we just used it here for the pulling test. Of course, people were a little bit worried about this big cavity inside. So the inclinometer is at the base of the trunk, monitoring what's happening with the root and soil connection, and the elastometers are placed along the trunk to monitor the fiber deformations. The basic principle is that we need on one side an understanding of how strong the tree is. And we want to understand how strong it is without breaking it, without damaging it. Normally, if you want to find out how strong a tree is, you pull until it breaks. And then you know. And this is basically a scientific way to get information about how strong trees are. On the other side, it's not enough to know how strong a tree is. We also need to understand what are the peak loads it is exposed to. So how strong does it have to be? Okay, because we know some trees are really weak, they can't withstand strong forces, and other trees are really strong. That's not enough information to give a safety statement or a risk statement. So the other side is the peak load, and in this case, the pulling test method or the static load test method is designed to compare, in the end, the peak loads exerted by the wind, because they are the strongest forces usually that trees are exposed to, and the forces work perpendicular to the stem. You know, we have gravitational forces like snow and ice, but just compress the stem and bend the branches. So as you see, this is not a method that is a universal method for everything. We are not dealing with gravitational forces usually, and as soon as we have to deal with gravitational, for example, if a tree is leaning or slanting very much, the entire thing gets much more complex. So there is always a certain task that you can fulfill with one technology, with one tool, and as soon as you want to use it for a task that's a little bit different, then you have to start and work with it. You can't just apply the method as it is on a slanting tree. If you want to understand how strong it is, I already mentioned that, we use the actual pulling test, the experiment, what happens when we pull on the tree and bend it. That data that we get there is then used and is basically compared to guideline values for the limits of strength of wood, for example, or generalized curves that can predict the tipping behavior of a tree, a typical tipping behavior. We don't uproot the tree, so we have to do an extrapolation, and the extrapolation serves only to establish an estimate of the tolerable loads. It's not an accurate prediction, but we have data that shows that these predictions are generally quite Good. On the other side, that's what Stefan already showed you just now. We have to estimate the wind load the tree is exerted to, and there, of course, it is even more difficult because you have to wait for wind until you can really get an idea if you're right, if you can to get a measurement of how long the wind really acts on the tree. The typical procedure at the moment is we measure the tree height and we scale a picture of the tree to this height. We do an assessment of site characteristics. We have to assess the structural parameters of the tree, and there are models for and for a dynamic interaction of the tree with the wind. So this is basically where we have a dynamic element in the analysis, whereas the static load test, as the name says, the pulling test itself is a static test. The dynamic elements in this method are only a part of the wind load assessment side. Why do we need a standard? This method has developed now for more than roughly 40 years, and there are new developments. There's a growing circle of users worldwide, and currently it's an estimate, I don't know exactly, but talking to people who train people or sell instruments to people with this method, it must be at least 300 users in at least 150 companies worldwide using this method. This was in Hong Kong, and we guess, and again that's only a guess, when I talked to Lothar Wessely the last time, we just put together our numbers and said it must be more than 30,000 reports on individual trees using this method so far. Why a standard by the SAG Tree Statics? What is that group actually? The SAG is short for Tree Experts Association or Corporation. Is a non-profit association, and we have currently 60 members. This was in Italy. There's Francesco here, there's Stefan there. You're not members yet, don't worry. You don't get charged your membership fees. We took this picture in our summer school in Italy some years ago, where we had guests, of course, because that's the idea that we're not only talking among ourselves, we always have guests, and we're happy about people who are interested in this method as well, because we want to promote these approaches that go back to this engineering idea of natural constructions, and we want to communicate these methods and their practical application among the tree industry. And the knowledge that we have as SAG among our 60 members, you can bring it down to really an enormous number of pulling tests and expert reports. Many people choose hold trainings and teach at universities or in private courses, and we are involved, have been involved, several of our people, in scientific studies on biomechanics. What we do normally, when we're not busy writing a standard, and I can really confirm that it is a tedious process, thing like that. Everybody who's involved with the standards here knows about that. We do workshops with specific topics. That was one of the first workshops with Australia. Do we have another replacement microphone? Probably not. Okay, but it works. It's fine. I was just joking. If it doesn't work, then I come back. We have had workshops on studies in wind tunnels, which is very different from trees in natural environment. The big advantage is you switch on and you have wind. Normally you don't get that. We had a workshop with Andreas Detter, just mentioned in Stefan's talk before, and Hans-Christoph Spatz, for example, and Karl Niklas talked to us about material properties in greenwood. And we were in France with the colleagues in France, in Nancy, talking about biomechanical adaptation processes. So all these are interesting topics for us as consultants, tree consultants, who want to make statements about tree risk in the end. The objective of the standards was to get a definition, the minimum requirements for this method, so to say, and it was supposed to serve as a guide for our members and other people who would be interested in understanding what this method of the static load test method requires. The contents put together by an international group in the last 6 years now, but it was finished last year, so it took 5 years. We have recommendations and requirements for the qualification of the user of this method, for the setup and implementation of the actual test in the field, the wind load assessment as one important part of this method, and the evaluation and interpretation of the data. So these are the 4 main paragraphs that deal with the method, and then the last paragraph sets out minimum requirements for how to present these results. Because what you see sometimes in practice, that somebody does a pulling test, analyzes a tree using this method, and then he gives a safety factor and says, that's it. Well, that can't be it, because there's a lot to it. There's much more than just the end result. And if you want to understand and really evaluate this result and implement it in your tree management plans, then you have to understand how this was done and whether it's really adequately done. So this is my daughter. That's why I'm still working. I have young kids. We just talked to Glenn that I will have to work for a long time. Glenn, she's now 6, and the younger brother is 4. So the next 20 years I will have to pay. It will keep me working. But visual inspection is not something for kids. You have to have a lot of experience with that, reading. And as long as we don't have artificial intelligence do it for us, we will have to do it ourselves. And if you want to work with a method like this, tree biomechanics is very important. So you need experience in understanding how trees respond. The engineering approaches, well, I'll just run through that a little bit because I'll come back to many of these points later. Place safety is something that I want to go into, and of course, verification of data. If you deal with data, you can't always run these confusing statistic analyses that Stefan has shown us, but you have to have an idea if what you get there, the signal that you get there, the data that is recorded by a machine, if that is actually telling you something. Because there will always be numbers coming in. But what do they mean, and are they actually correct? This is what you have to understand when you apply a method like this. One thing that's different in pulling tests is that you're dealing with high forces. And I don't know any other method where you can kill a person when you really, well, you can drill into someone's heart, of course, but that would be on purpose. But there's hardly any other method where you can damage a tree, break it, uproot it, and where you can hurt someone who's just passing by. So in the pulling test method, we have to have safety precautions. We have to have good configurations of our devices. Basically, it's like a rigging setup. You have to build this experimental setup like a machine. And you have to be careful about what's happening around you. And it's not just you who is in danger, that you step on the road and are being driven over, but you could actually, with these high forces, cause severe damage. Therefore, you always also have to monitor the tree while you're pulling. Any weak spot must be monitored so you can ensure that you're overloading the applied loads, be limited to a certain level so that we can be sure that all the responses that the tree shows are reversible and we are really in a non-destructive range. For example, the change of inclination at the root plates, the rotation, so to say, that we do at the plate is limited to 1/4 degree. Because we know studies that we can be quite confident this change in inclination is not damaging the root system, and it's reversible. The same is true for the fiber strains. When we compress the fibers or stretch the fibers, there is not just one limit, there is different limits in the situation, and you have to be familiar with that. And we also sometimes in some methods apply a defined fraction of the wind load to make sure that the results are really usable. I'm running a little bit out of time, and I don't want to extend it too much, so excuse me if I'm going a little bit faster, because these are just implements that you have to consider when you set up a pulling test, because in the end we want the balance between the strength, how strong is the tree, and the load it is exposed to. So to get the least favorable situation, we use the strongest wind impact and the lowest strength. And this here is just an example from a practical experience that sometimes when you tender for pulling tests, you actually give the cheapest consultant the job to test your trees. You sometimes don't get the result that you really want. If you pay peanuts, you get monkeys. So what happened here is that the trees were supposed to be tested because the roots had been cut. And of course, the cheapest way was to pull this tree to that tree and this tree to that tree. So not perpendicular to where the roots were cut, but parallel to the cutting line. And the result is just not worth anything because you didn't test the favorable direction. When the wind comes from the side and the roots are cut, these trees may be responding completely different than they responded during the test. When you're measuring on the tree, measure the response, you have to be sure that your sensors pick up what you really wanted to measure. For example, in the inclinometer, it is essential that the inclinometer is positioned really at the base of the stem, because you can imagine if the stem is bending and you place your inclinometer higher up, you pick up the bending of the stem, but you think that you're picking up the movement of the root system. So these are very important criteria to judge whether a test is actually usable or not usable. Or in this example, the fiber strains here and the fiber strains on this position actually give you the compression or the extension of the fiber length. But if you place your sensor from here to here, the change in curvature brings the two positions closer to each other without bending or without compression or extension of fibers. This is what we call strainless deformation. So if you want to get rid of the tree, you place your sensor here because you generate high compressions that are not compressions. They're just changes in curvature. Now it's really giving up, I think. Do we have a replacement? Not yet? Okay. Okay, that works again. Also, sometimes you see, because people don't have time for the test, they offered it for a cheap price. Then you have a tree like this with a 7-meter long cavity next to a highly frequented road and 2 sensors there. Of course, that gives you data, but you cannot be sure whether you got really the weakest position. In modern technologies where we have constant data sampling, we see environmental effects like wind, for example. These are examples where we can see that it was a windy day. This is important information for me if I want to judge whether I can base my recommendation on the results of this measurement. And this is another of Stefan's diagrams where we don't know what he has smoked before he did it, but it gives you an idea. Well, we know each other for a long time. Where is he? Here's probably his... Oh, yeah, there you are. Sorry. It's all recorded right here. You can sue me for that later. This gives you an idea that it's important to understand how much data you got. It's like shooting with bow and arrow. If you shoot with bow and arrow for 100-meter distance and you had too much coffee and you're shaking, you will probably miss your goal. But if you stand 1 meter before your target, calm hand, you're probably going to hit. So this is about measurement technologies and background. Let me just check how much time we have. Not much. There's a workshop tomorrow. I'm just doing advertisements now. There's a commercial break. So tomorrow we have more time, especially also for questions, because what I'm saying now is probably generating a lot of questions and we may not have the time to deal with it now. What I wanted to show you here is that, for example, the wind load assessment is something that deals with a very complex interaction of wind and tree. Wind is complex, the tree response is even more complex. But in order to get a working method, we need to simplify things. The same as the engineers who have to assess the wind forces acting on a building or a bridge. They have to simplify. They cannot build the bridge and wait for 10 years and measure what's happening. They have to do this in advance. So the same is true for us. We have to get an idea how tree and wind interact. And for you to understand how that works, the easiest is to understand wind as a form of energy. If you stand in a storm, you can feel the energy. Feel the energy, that's a nice saying. But the trees are absorbing this energy, and as they absorb the energy, forces are exerted on the tree, on the branches, on the leaves. And what happens is that the tree's structural elements, the branches and leaves and everything is starting to move. And as soon as something starts to move, we can dissipate energy. We can get rid of energy. We can shake and move and bend and twist. And all this happens, for example, with the strains, the wood that's bending and compressing fibers, the torsion that's happening. Torsion is probably the most effective way for the tree to get rid of energy. Get rid of energy. So torsion, in my perspective, is not a problem, it's a solution. I know many people see torsion as a problem. Trees have used torsion to get rid of wind energy very effectively. And the same is true for what's happening when the tree moves in the ground. If the roots are moving in the soil, humid, wet soil, they can get rid of a lot of energy, which is called a mechanism that's called hysteresis. And we quantified that in one experiment where we could show that even at low inclinations, the tree can 20 to 30% of the energy that it was exposed to into the soil and get rid of it. It's basically a bungee rope, dissipating the energy instead of putting the energy into high forces and act on the tree. So our methods have to do that. They have to be able to illustrate that, to replicate this, which is, of course, different from the normal engineering approaches. A building does not move in the wind, usually. Well, it shouldn't. I hope this one doesn't. But it's completely different from the behavior that trees are doing, but we can use the models. If we want to use the models, they have to have certain capacities, otherwise we get a completely wrong result. That's one example for two different methods in engineering that are used for wind load assessment. One is used for a building that doesn't move and has a regular shape. You just take one wind speed at one defined height and you calculate the pressure per unit area unit, and then you multiply the area that's exposed to the wind with this pressure, and you get the wind pressure. If you do that with two trees, like this, you would get exactly the same wind impact on the two trees. And that's not true. The tree that has the higher where the big parts of the crown are high up, where they're exposed to high wind speeds, this tree will receive much more wind forces, much greater wind effect than the other tree that has a tip up there. So we have to use complex model, which is also present in the civil engineering codes, but this would be a model that is suitable for trees and the other is not suitable. Also, we need to define a reference storm. You all know that. If we say the tree is storm-proof, what does that mean? Is it still standing after a tornado or a typhoon? We call it storm-proof. It's not storm-proof. It's just sufficiently storm-proof for us to say, okay, we can retain it. Anything that may cause failure in this tree is then called an act of God, something that was unexpected. And in your report, you said the tree is okay and now it's on the ground. You have to explain that to your client. And that has to do something to do with a reference wind speed. We're not testing the trees for any wind speed, but for the stormy winds that we have to expect under normal conditions. And we can use approaches that are established in civil engineering, like, for example, the terrain categories that give us an idea of the effect of the terrain around the tree. But that's not enough, because trees have very different structures. And the response of this tree on the right side to the tree on the left side will become different, because it's a very different structure, and we have to take into account the dynamic properties that are different for these two trees in order to get to a reasonable assessment of the wind load. Trees are flexible. They have a porous crown. Trees may be located in a protected site or in an exposed site. Trees may be standing alone or in groups. All these things are not relevant for civil engineers. But if we don't take it into account when we judge trees, we will get a lot of unnecessary fellings, or even maybe get false assumptions on situations where we think the tree is protected, but it's actually not. I think I don't have enough time to completely go through what I wanted to tell you. So this is the cliffhanger for the workshop tomorrow. Can spend more time. Do I have 5 more minutes, or actually not?
For you, definitely yes.
No. There's no exceptions. This is just a graph. It goes back to Ken James' work. Ken James came up with the idea of this ball of string. And these are two trees where I generated this ball of string. Basically, we measure these trees' responses to wind. And the blue line is, so to say, a track of how the tree moved in the wind. It's the bending response in the stem that we record. And you can see that there is a maximum response somewhere here. But it's not one constant blow where the wind comes and blows the tree to this maximum response. It's a sequence of gusts, many, many gusts. And these loops here are just these movements of the tree until he suddenly, at one point, reaches the maximum response. And then it immediately goes back. But if the tree is not strong enough to withstand this maximum impact, then it may break. Or it may be irreversibly damaged and lean afterwards. And this is a dynamic response, but you can actually mimic this dynamic response with what we call the static equivalent wind load. Because now if I use a pulling test and I pull the tree to this position with my winch, I can measure the force that is equivalent to this dynamic response. And this is not something that the tree people have come up. This is a model that's present in civil engineering. It's called a gust response factor. And this is something that is really suitable for us when we work with trees, and we need that adaptation for a dynamic structure, the tree, in order not to completely underestimate the loads that the tree is exposed to in wind. Thank you very much. I underestimated how quickly the time passes. Thank you.